Greeting everyone. In previous class, we have discussed few questions from conceptual questions on resistance, and today we are continuing that segment only. And today we have very special question for you. This is our J advanced question. This question will be not exactly that question; it will be a little bit different from that, but the core concept will remain same. This question was in 2020. What I am going to ask in this question that you have a semicircular disc of width t. In that question, what you had is they have given you the value of current, and they had asked you to find the value of potential difference. But in this question, I'm asking you to find the resistance itself, and I'm not giving you the value of current because first of all we are focusing on resistance part. As we will get clarity on this concept, we'll come back on this question again and we'll discuss the exact same question from advanced. But even in that case, even in advanced case, the half portion of the question is still same. Means in that question also you have to find the value of resistance, that we are going to find it. So again I will give you this picture, and you can see from this picture, this is our semicircular disc of inner radius R1 and outer radius R2, and the width is T. The top view is this, and I want you to try this question, and don't continue without giving any try. Just try to solve this question on your own, and let me see if you are able to do it or not. And if you want a hint, I'll give you a hint that you can take a semicircular stick, and then you can do it. Give it a try. Okay, I'm thinking and I'm hoping that you have given it a try. Now let's see how we will do it. Okay, so how we can do this question? Just like I told you, we can divide this whole segment into very, very thin disc, and we can evaluate the resistance of each disc, semicircular disc, and we can get the idea of total resistance. Okay, so let's see. Like this, and another one like this. You can ignore about this part, this red one. Okay, somewhat better. So we have taken what? Okay, so in this picture you can see we have taken an elementary piece of this elementary piece of this conductor, and if you see from this picture how we are taking it, it is just like this. We have this conductor and this much section we are taking. I'll mention it with some different color so it is clear to you. Okay. So very thin segment we are taking of dx something width, right? So this has width of dx, right? And it will be like this. Pardon my drawing. Okay, just something like this. So you can see the inner and outer radius of any element will remain. Inner and outer the radius will change, but this width will not change. This dx will not change. And if you see, the current is going from this section, current is coming out from this section. Means each elementary part will be in your parallel. Why? Because if you see from the picture, you can see the current is going from this segment and coming out from this segment. We can say this whole section will have some potential V1, and this whole section will have some potential V2. That means each elementary section will have some resistance, and all of them will be in our parallel. So this is the main thing from this picture you can get. And let's say the resistance of this is dr. So to calculate the total resistance, to calculate the equivalent resistance, what I need to do, my total equivalent resistance will be integral of 1 by dr, not dr, it will be 1 by dr, because all the element will be in our parallel. So let's calculate how we can get the resistance. In this question, you have to assume that current is uniformly divided, or it is flowing radially. So you can solve this question, otherwise it will be difficult to solve. You can imagine that total current is 10, so it is 0 point something on this side, 0 point something 2 in this way. So each element will have some current, it can be same, it can be different. And let's say the radius of this segment is smaller, right? Now let's see what is the radius, or what is the resistance. Resistance is what? Rho L by, so what will be L? So total length, how much current is traveling? This much length means semicircle, that will be our pi r, okay? And area, what area current is going? You can see from that picture. This area current is traveling, right? This area. So this is dx and this is t. So area is t dx, right? So this is what we have to do. So we can see the total resistance 1 by dr, we have to write inverse of this. So this will be also inverse. So it will be our t dx over rho pi r. See, we are integrating in terms of x, and we have variable r also. But this we can deal it like simply, we can think it like, again you come in this picture, you can see like, let's say this radius will be r1 and this is your dx. So I can do it like this also. I can make this, either I can make this as x or I can write this as dr. Whatever suits, you can do it, right? So we can say you went r distance in this direction, you took dr width of element, right? Now you just need to do what? Once you adjust the things, let's write it dr, right? Again here also we have to adjust little bit. Okay, so we have to calculate total resistance. So we will go from what? We are integrating in terms of r, so we will go from r1 to r2. R1 to R2, and that's it. Just now you have to integrate. This will give us 1 by R, and this will be our what? Your T is constant, rho is constant, and pi is also constant. We are integrating in terms of 1 by dr, R1 to R2. So if you integrate, you will get ln R. It is ln R, and you will have what? Lower limit and upper limit, right? And you can substitute the limits. You will get what? 1 by R equals to T by rho pi, and this will be our, I can simply write it upper limit minus lower limit, so it will be R2 by R1, right? And then you got the value of 1 by resistance. To get the resistance, you can just simply do what? Inverse of it. Understood how we are doing this question? Again, I will tell you how we solve this question. To solve this question, we went r distance and took an elemental semicircular ring of width dx, radius will be r, right? And this is always going to be what? T. So we took this element, this element, this element until we reach to this point, from R1 to R2. And because each element will be in parallel, so we will not integrate 1 by dr. We will not be doing integral of dr. We will be doing integral of 1 by dr. So because they all are in parallel, and simply at the last you can do just what? You can do inverse of it. That is your answer. In the advance, you have to evaluate the resistance then you have to apply just the Ohm's law to get the value of dV, delta V. So I think that is also easy. Once you know how to find resistance, current was already given, you can just simply calculate the delta V. Right? All of you understood? I'll give you one more question. I'll let you try. Okay. So in this question, what you have here? Okay, so you have a conductor, a solid conductor. This is our elliptical. This is elliptical shape, right? So in this question, what you have? A conductor for which the cross section is elliptical. This is your capital N, this is your capital B, or you can switch, although it doesn't matter much. Let's write it A and B. So this is your elliptical cross section, this X is your Y, this X is your X, right? And current is entering in this phase and coming out from other phase, and the length is L. Okay, so you have to find the resistance. It is rho resistance. The only difference I am giving you here is this coordinate is our 0, 0, 0, and the resistance is equals to alpha time under root y. Okay, alpha time under root y, where alpha is some constant. Alpha is some constant in this case. And what you have to find? You have to find the total resistance. So this question will be your homework. I think you can do it. In this question, you might not even need to take element, or maybe you need to take element. The only thing here is, in all the previous questions, your resistivity was constant. But in this case, you can see your resistivity also depends on y. And I will give you a hint, you can use the equation of ellipse to get the answer. So this is your homework question. I hope that you can solve this question. Okay, you can take a screenshot so you can have this question. Okay. Now we all understood how to solve the questions. Now again I'll give you one more question, last question. That is very famous question. It has been in many books mentioned. It has been mentioned in many books. So you all must be familiar with this question, and if you are not, then you are going to get familiarized. Okay, so in this question, you have two-part question. Case 1, this is your cylinder. It has cavity from inside, a cylindrical cavity it has, right? And there is two radius, R1 and R2. R1 being inner one, outer one is R2, right? So this is the question. You have to assume that current is like in this case, first case I am going to give you. So current is going like this and coming out like this. Okay, assume that current is going to distribute radially, and it is given the resistivity is rho. You have to find the resistance. Okay, I am hoping that you all know, if I say that current is going from the top phase and coming out from the bottom phase, you can calculate the answer. That is not difficult one, so you can do it by yourself. So this question is your last question on this segment. You can evaluate the resistance of this solid like hollow cylinder for which inner radius is R1 and outer radius is R2, and when current is going from this side and coming out from this cross surface. Only thing you have to assume that current is distributed radially, and I'll let you try. And don't see the solution until you give it a really good try, because this question is board standard, so it should not be difficult for you. Okay, I'll let you try. Okay, now see how we can do this question. I'll give you the fair share idea. I'll not solve this question entirely because this question is fairly easy. So I don't think I should be solving this question completely. Nevertheless, I'll give you the idea. So this question you have, I'll give you the idea how to solve this question. You have to find the resistance. The idea is pretty simple. What you can do is take elemental section. Again, as I told you, the current is uniformly distributed. Let's say I took this elemental section. This color is already there. I took this elemental section okay, so this is your this is going to be your elemental cylinder. Okay, so you can solve this question. I just, like I told you, assume that current is uniformly distributed. So let's say the radius of this section is smaller, and this section, the width of this section or the thickness of this cylinder is dr. Are you getting what is this? See, I'll show you here what is this. We have taken elemental cylinder of very thin width, just like this. This type of elemental cylinder we have took. So this width is your R, this width is your, at the end, till this point it is your R plus dr, means this thickness is our dr. Okay, so it is hollow. If you take this section, so current is traveling from the picture. You can see the current is going to travel like this. So it is traveling only dr distance, or what distance it is traveling, and what cross section it is traveling, you can see from the picture. And then you can see if current is going like this, so each elemental will be in your series. So what you can do, you can just integrate dr, and you have to find what is the value of dr. You can see from the picture, the length which is currently traveling is dr only, right? The length current traveling is dr only. Resistance is what? Rho L by, so rho L is your dr. A is what? The cross sectional area. Cross sectional area, you can see what is the cross sectional area of cylinder you can have. It is going to be just, if you cut it from the middle, it will be just like a rectangular sheet. So the cross section will be your just 2 pi r L, and then you can simply integrate from R1 to R2 and you will get the answer. So you can complete this question and the previous question also. And after this, I will be attaching some segment of Ohm's law experiment. You can have the idea of Ohm's law from that experiment.